Okay, so let's start. From last time, we talked about the quantum Fourier transform, and we're gonna see why quantum Fourier transform is useful in order to find out the period of a function. So first, let me restate the definition of quantum Fourier transform. So it's a quantum gate, which means it's a linear transformation. So all we need to know is how does this quantum Fourier transform act on base state. Let's say x is a base state of n-qubit state, and it is defined as this long superposition. So just remember it, just memorize this. Okay, so here is our new question. Computational question, of course. So let f be a function that sends n-bit string to 1-bit string, and we want to find the period. And be a period R, periodic function. Period R such that R divides 2 to the n. So R is just some power of 2's. And how do we find the period? So in classical ways, there's no way you can find the period until you see all the values of function for entire inputs. Because even if you see some numbers are iterating, because you cannot conclude right away, because at the next round it might differ. So here is gonna our quantum circuit to find the period of this situation. So so I think I should write a little bit with big letters. Because last time I checked the video, I think the resolution is not good enough to see all the writings. So let me gradually make it bigger here. So 0, 0. So whenever I write Hadamard here, so it's acting on the n-qubit state. So you can imagine that there is a n Hadamard on the input register, and there is an oracle. The oracle is the same thing. So let me just draw the oracle here. So we have oracle always comes in with 2 to the register, 1 with input register, the other is an output register. Doesn't do anything on the input register, but changes the output register. So basically, it adds fx to 0. So after passing the oracle, we pass the input register through the quantum Fourier transform, and then we're gonna take a measurement on both registers. So measurement is the end of every step. So we don't put more lines above after this measurement, some measurement symbol here. So let's see what happens. So this is 0, 1, 2. So let me write up to 2 here, and then 3 here. So let's try to write all the quantum state here. The psi 2 is going to be 1 over 2n over 2 x from 0 to n minus 1 and xn times f of x, right? So this summation is not coming from the quantum Fourier transform, it's coming from the Hadamard gate. So every Hadamard gate makes a superposition of equal states. So after passing through the oracle, we have changed the output register. And after passing quantum Fourier transform, we're going to apply quantum Fourier transform each of these base states. So let me write it step by step here. So then 2n over 2. Oh, so I need coefficient. And exponential. Okay, so that's the psi 3. And let's, so we don't know what this is about. We don't know anything about this. I mean, we cannot make it simplify further because we don't know anything about the function. But what we want to know is what happens after we take the measurement. So let's say, so this is usually, I think I already mentioned it several times that, so this means that it indicates the readoff after the measurements. Let's say I read M for the input register after measurement and J after measuring the output register. So M is n-bit string and J is 1-bit string, 0 or 1. So let's say I read M and J. So I want to see what the probability of that outcome. Okay, so how much how much probability are there so that I can read M and J. So this is the probability. To observe M on the input register and J on the output register. So all I need to do is just pretend that fx is just J and y is just M, and then kill everything else. Or I could just take this raw to take a measurement. So all I need is I want to take J on the output register and M. So M is a bra of n qubit state, so I need to put n as a subscript and take this bra, so center product of bra. So this is for the input register and this is for the output register, and then apply to psi 3 to find the probability. Okay, and also I need to take the square root. So let's try to compute this. Okay, so what is it? So when I take the bra of M here, everything is cubed except when it's M is, Y is M. So it's 2n over 2 over 1 and x from 0 to n minus 1. And so there's another 2 to the n over 2. So I get this 2 to the n. And exponential 2n 2 pi I x m. So of course my is here, but it's 1, so I can get rid of it. And also fx equals to j, but it's also just 1. So what I need to do is okay, let me not erase that part. So let's put this part here. So well, I want to compute this, right? I want to compute this. So this one is only 1, and only when f of x equals to 0, f of x equals to j, and it's 0 when it's not j. So even if I take a sum of x from 0 to 2 to the n minus 1, I only want to take when f of x equals to j, right? So I don't have entire sum. I only have the one that has f of x equals to j. So I'm going to write it down as the following. So it's 2 to n here, and big sum of just x. So where, let's see, f of x equals to j. So take only x satisfying this equation. and exponential 2n 2 pi I xm squared. Okay, so that's PJM. So at this moment, let's give an example here. So I can carry on with the symbols, but I think we need to see some concrete examples. Just an example. So suppose that I have n equals to 3 and r equals to 4, which is 2 to the second. So we have a period of 4 on the entire length of 8, right? So and also let's say so when x is from 0 to 7, let's assume that my value of f of x is 0, 1, 1, 0, and 0, 1, 1, 0. So you see that there is a period of 4. So suppose, so I've done this whole computation in quantum circuit, and I took a measurement, and I read m equals to 6 and j equals to 0. So let's try to find out the probability of this observation. Okay. So I'm going to plug that in here. So as a notation, let's write as fx of j to be either 0 or 1. So it's going to be the same as j inner product with f of x in the bracket. And this is going to be 0 or 1 if f of x is equals to j, then it's 1. If it's not equals to j, it's 0. So just abbreviate notation here. So let's try to compute this. So what is it? So I only want to take so forget about notes. So let's try to do it. So n is 3. So I have the 2 to the 6, and here, so I have the period of 4. So it's one period is doing running twice. So I can so it's going back to the beginning here, the first line, not in the second line. So that's what happens. So let's say k from 1 and x from 0 to r minus 1. So it's r equals to 4, it's the 3. So 0 to 3. So 0 to 3, 0 to 3, it's running twice. So k is the index of period, and x is the index inside of the period. And also, in that case, maybe I've used, let's use different symbol here. So since I used x, so what other symbol might be better? So let's see. Let's say y. So x is now, what is it? 2n, 2 pi I. X is now r k plus x, right? So k is how many times you have run the period before, and it's only 2. There are only 2 periods running entire sequence, and x is in how many, in what index are you at? Sorry, y. At what index are you at inside of the period? So that's your x, right? So I just split it, the first big sum, into 2 sums here, and m, right? So and then don't forget that j bracket fx, so it's going to be fx j here squared, right? So now I can split this sum into further splitting means that I can rearrange our summations. So it's 2 to n, and so maybe I just write down 6. Let's see. So I want to split the exponent rkm and ym. Okay, so rkm doesn't depend on y, so I can take it out. So it's going to be exponential 2n 2 pi I RKM. So basically it's actually RMK because R and M are constant. K is only one that's changing here. And Y from 0 to 3, right? So we have exponential 2n 2 pi I and ym. So my and fxj, okay, square. All right, so now if you see this thing here, over here, so we know that R, let's see. So we know that M is 6. I mean, that's how we assumed here. So we know that this is going to be just 6 RK, right? So 6 RK. And I also know what R is, right? I know what R is. I know, and because this is just an example, right? I want to see what happens when I read M and J as that number, and M is 3. Okay. So let me just put 3 here. So M is also 6 here. Y is here. And look at this sum here, right here. So what do you see inside of the exponent of exponential? So you have 8 in the denominator, and on the numerator you have 6 times 4, which is 24. So 24 over 8 is 3. So it's basically, it's an integer multiple of 2 pi I. Right? What is the integer multiple 2 pi I when you take the exponential? What is the integer multiple of 2 pi I when you take the exponential? 1, yeah, it just disappears, right? So it disappears. So it's all 1. So it's just 2 here. So because we're taking k from 1 to 0 to 2, right? So we have 2 times of something over there, right? With all things here. Okay. So, so in that case, you don't expect that this probability to be 0, right? So there's something out here. There's some summation out here. By the way, let's change the situation a little bit. So it's not 0, maybe. So I'm not saying definitely because I don't know what f of xj could be. Because f of j could always 0, then I don't see anything here. So, however, let's say I observed 1, okay? So I observed 1 and j equals to 0, right? So then what happens? So everything is same, n is 3, r is 4. The pjm is now what? 1 over 2 to the 6, and k from 0 to 1, exponential 2, 3, 2 pi I. M is 1, so just 1 here, and R is 4, K, and something, right? Then what is this sum? So what happens to this sum? So yep, R, K, M, R. Yeah, so what is that sum? It's a geometric series. 0, yes. Why? Because k from 0 to 1, so even though I wrote this way, let me change the notation. 2 pi I times 4. It's times k, so times k, right? So this is your common ratio, right? So how do you do? So it's a simple sum here, though you can use the geometric series formula. So it's 1 minus the common ratio, whatever that is. And what goes on the numerator? It's the common ratio to the power of entire number of summands, right? So we have exponential 2, 3, 2 pi I times 4 times what? 2. There are 2 sums. So when you do that, so 8 over 8, this cancels out. We have 2 pi I. Exponential 2 pi I is 1. 1 minus 1 equals to 0. So it's 0. So what does that mean? There's no chance you observe m equals to 0 and j equals to 0. M equals to 1 and j equals to 0. So actually j doesn't matter, right, in this case. Only m changes the possibility. So when m is 1, there's no chance to observe m equals to 1. So what is m? It's the output register. So it's the read of the input register. So you kind of know what's happening here. See, it's only when you have r times m equals some integer multiple of your entire the number 2 to the n that your probability doesn't become 0. But if it's not, which means that if r times m is not an integer multiple of the 2 to the n, then your probability is 0. So let me summarize this. So if, let's see, Rm is an integer multiple of 2 to the power of n, then Pjm is going to be 1 over 2n. So now we can work on with the symbols because we're not assuming specific numbers here. So as I said, k is just a number of iterations of period inside 2 to the n. So how many iterations do we need? We need 2 to the n over r iteration, but we are indexed from 0, or just take minus 1 outside. And then for each period, I think I mentioned this as y before. So your index runs from 0 to r minus 1 for each period. And your coefficient, you look at the original equation there, is 2 pi I and rk plus y, right? And then fxj squared. And then again, 2 to the 2n, take a sum from k for k and split the exponential 2n 2 pi I r. I think I forgot something, right? Rm, I forgot m, right? I need m here. So rmk times y from 0 to n minus 1 and exponential 2n 2 pi I my fxj squared, right? So it actually this doesn't matter. What matters is this part. So since Rm is an integer multiple of 2 to the n, what happens here? So this everything is just, you see, Rm divided by 2 to the n is just integer, right? So it's just 1. Everything is 1. So how many times do we have in the first summation? 2n over r. So 1 over 2n over R squared. Remember that this whole thing is squared. And something. My fx j squared. Okay. So this is 1 over R squared of everything squared. So we have this much probability, and it's not 0 unless everything is 0, right? So it's something, I mean, it cannot be 0. Like if every, well, I think it depends on J, but at least let's say the value of function is not constant, and we didn't choose J. I mean, if it's not constant, then at least one sum of this big summation is not 0. So therefore, you will get some non-zero probability here. So what does that mean? So if you observe something after taking a quantum circuit, and then what you read off is M and J, then you can conclude that Rm is an integer multiple of 2 to the n if M is the measurement outcome of the input register. Right? So what does that mean? We don't know what R is. Remember, we want to find the period, right? All we know about the period is that R is just a power of 2. We don't know what R is. So suppose that n is quite large. There's no quantum computer of this much qubits, but let's pretend that we have this much qubits, which is quite large, like 2 to the 1,000, 2 to the 2 to the 10. I think it's, can you? I think it's impossible to mimic in your classical computer of this much size. But anyway, suppose that you have this much qubits, and you want to find out the period. So I took a measurement, M1, M2, and let's say Mn. So I don't want to use n here. Let's say Ml, right? So let's say first M1, I can factor it out. I can, because it's a number, so probably it's gonna take a long time to factor. But anyway, I can factor somehow. Let's say I pretend that I factored it out to 2 to the power of n1 times, let's say n1. Okay, so n1 doesn't contain any 2. And let's say m2 is also factored out as 2 to the n2 times n, sorry, not n here. So that's e1, so it's e2. Okay, so and also into 2 to the nl times el, right? So you can go forever, but let's say I did for sufficiently many times. So L is quite large, and I have sufficiently large number of data to infer what the R is. So how do you conclude what R could be? It's not 100% correct, but let's say you take the minimum of this N1, N2, up to NL. Let's say this is N0. Okay. So what's the R rate? What's the period? What could be the period? Sorry. In this case. So for example, let's say if this was 7, right? You can find the minimum easily. If this was 7, what is R? But not definitely, probably. See, every time I take a measurement, I know that the period r times that number must be some integer multiple of 2 to the n, right? So 2 to the n, 2 to the 1024 is, so times some number, whatever, k1, equals to r m1. So r times 2 to the n1 e1, right? So k1 should be e1, right, in this case. So, or k1 could have 2's. So sorry. So anyway, so r should be what? At least bigger than what? Yeah, 2 to the 1024 minus n1, right? So it gives the lower bound. It gives the lower bound and lower bound. I mean, you can have a large period, right? Like if you have a period, I mean, if this is the period, you can say this is the period. But what I want is find the smallest period, right? I don't want the big period. So you can find, I mean, everything is period if you take the multiple of period. So you can find a period by taking one measurement, but that doesn't guarantee the smallest period. So you have to keep doing it until you convince that this must be the smallest period, right? But by taking just one measurement, you kind of know immediately what the period should be, right? So if you take this much measurement and you get the 7 as the smallest number, which means that 2 to the 7 was the smallest, you can observe as a factor of this m, then r must be this much, right? All right, is it the opposite? Let's see. Not minimum, is it maximum? Yeah, I think it's maximum, right? If it have a, let's see, a larger one. Yeah. So you have the maximum, right? If you take the maximum of this, right? Let's say you get the maximum of 7, then the smallest period you can get is this much, right? All other period, say all other possible period must be bigger than this. Actually, it's a multiple of 2's. So it's not 100% accurate, of course, because maybe, who knows, the next time you take the measurement, you get L plus 1 equals to bigger than 7, right? So then you get a bigger number, a smaller period. But you can get, I mean, every time you do this, since I know that there is always a period coming out, so in a reasonable reason, I mean, we can't compute the probability here yet, but reasonably accurate sense that we get the period for sufficiently many times of taking a quantum circuit, right? Makes sense? So how do you know it's a period? How do you know it's actually a period? Well, you have to take the actual numbers. You have to see the functions, right? But it's better than, so in this case, I think I kind of exaggerated. So maybe 2 to the 1024 is big enough, too big here. So let's say, okay, 782. So minus 782. Let's say we observe the maximum of 782. Let's say then the period must be how much? 242. Yeah. So 2 to the 242. And I think it's probable now. I mean, if you want to go through all the numbers of 2 to the 1024, it's too much. But now you just need to check the value of function up to 0 to 2 to the 242. 242 is not much, right? It's possible, right? I think it's possible. So anyway, so if you go through all the numbers classically, and then you could observe that there is a smaller period, right? But that's okay, because I didn't have to go through all the numbers 2 to the 1024. I can reduce the computation down to this exponentially small, right? So any questions? Does it make sense? Yes.
Just a little bit of confusion. What is the K1?
K1 is just an integer. So because every time you take a measurement and you observe m, it means that Rm is an integer multiple of 2 to the n, right? So that's the integer.
If you wanted like 2 to the 4, for example, then is there any chance to that we have to see until to the 246 or so?
So sorry, say it again.
So like if we have P1 equals to 4,
Yes.
so then the R would be like 2 to the 246.
No. R is, we assume R is divisor of 2 to the n. Yes, that's our assumption. Yeah. So we know that period is within our data. That's our assumption. We just don't know where we have to cut it. Any other questions? Yes. Okay, so yeah, so let us think about this for a moment. So I thought it was a minimum, but now I thought it was actually maximum. So let's pretend that we actually done this here. So let's say n equals to 102, and 2 is 782. So say I have 2 observations. And the first observation tells me that 2 to the n divides r times m, right? So m is 2 to the power of 102 times some integer, right? And the second observation says 2n divides r times 2 to the power of 782 e2, right? So I know that n is 1024, right? And now the e1, e2 has no 2 factors in. So r in the first case, is bigger than 2 to the 124, 102, right? So bigger than means that the power of 2's in R must be bigger than 1024 minus 102, right? So at least I know that the period is this much. But the second one says that R must be bigger than at least 1024 minus 782, right? So if R is less than this, then there's no way you can divide 2 to the n by this. To divide this by 2 to the n, right? So this is 2 to the what? 242. Right? So this one is 2 to the 229, right? So this one tells you that the period is this much. This one tells you that period is this much. So which one is the real period? This one is the real period, right? This already is the multiple of this, right? You want to find the smallest possible period. Yeah, so I think the maximum is right. You want to go for the maximum. It makes sense? Yes. Oh, wait. Okay. So, that's right. So we have, yes. So we have a constant R. R is the constant. So let's see. Yeah. So yeah. So this one tells you that R must be bigger than this. This one's R is bigger than this. Then if R is this small, then this is not true, right? So so I think, sorry. So yeah, the first idea was right. So it's a minimum, sorry. So we want to go for the minimum, right? So if n is 102 and the n2 is 782, then yeah, we have to conclude that R is this big. This is the case. So if you minimum, yes, yeah. So 102, 102, yes. So this is what this one is right. Yes. Sorry for confusion. Yeah. Any others? So now something is weird because I have data. Okay, so having 2 to the n number of data is okay. You can split the data somehow into 2 to the n pieces and take the value of function, right? But why can we just, I mean, how can we find the period which is not a power of 2? So in this case, we assume that the period r is dividing 2 to the n. That means r is always 2 to the power. But that's very rare case. Like there's only n number of possible choice of radius, I mean period, entire 2 to the n numbers, right? It's just finding very small chances. So the question here is, how do we use quantum Fourier transform to find any period in 2 to the n data? So that's our next task. How do we use quantum Fourier transform in that case? So we're gonna do similar thing here, but let me draw the same, almost same quantum circuit, but slightly different order. So we have the input register and output register, Hadamard, and we still have similar situation, but not exactly same. So instead of having a function sending the n-bit string to a 1-bit string, we have n-bit string to go to n-bit string in this case. Okay, so the function is this, and we want to find the period. The situation is a bit more complicated, and this is more appropriate in a context of encryption and decryption situations, because we want to decrypt your string. For example, let's say one character, it's a 8-bit string or something like that. You want to change it to another string, right? Another 8-bit string. So you don't want to decrease the size of a data, which means that it will lose your information. So you don't want to lose the information, you just want to change the data, but we want to find the period in order to decipher sometimes. So everything is same, but I just want to slightly change our the measurement component here. So instead of applying quantum Fourier transform right after oracle, I want to measure the output register and then take the quantum Fourier transform and then take the measurement. So let's say C1 and C2. So that's the measurement outcome. And see what happens. So after taking the measurement on output register, let's call it psi 3, is going to become the following. So we suppose that our measurement outcome is y, and let's say, since this is a periodic function, we know that this y is a value of function and it will appear several times in the entire sequence. So let's say f(x0) x0 is the first number that has the same, the value of function same as y. And for the next, let's say r is the period, which we don't know, is the second number, and fx0 plus 2r, and so on, plus m minus 1r, and all this equals to y, okay? So then what? Since we already took the measurement on the output register, everything is killed except for the output state equals to y, right? So we don't even have to record that case. All we need is to just mention what's inside of the input register. So how many are there? How many quantum state are there in the input register after taking measurement? There are only m number of quantum states, because x0 plus r up to x0 plus m minus 1r is the only quantum state survive, because that's the only case when you have an output register equal to, before the measurement, ket y, right? So let's get k from 0 to m minus 1 exponential. So don't forget that we already so we didn't take we didn't take the quantum Fourier transform. So we just have x0 plus kr, and that's an n-bit string. So it's an n-qubit state, and that's it, right? So and then after that we take the quantum Fourier transform. Let's call it psi4 and see what happens. 2m, and so do you understand why we have this coefficient 1 over square root of m? No? So originally we had how many? 2 to the n base states superposed after this Hadamard gate, right? We took a measurement and we killed everything except when the output register is equal to ket y, right? So it collapses to the state to a superposition of the remaining basis state. But think about the probability of each base state before the measurement. They were all equal. The chances of observing each base state on the input register before the measuring the output register were all equal, and their coefficients are always all the same, right? After taking measurement, you collapse it, and you collapse it into the same state, right? The same probability, right? So there are m base state remaining, and m base state has the same probability of observance before the measurement. Therefore, after the measurement, they are collapsed into the state where the probability of observance of remaining quantum state are also the same. So there are m. So there's no other way you can change the coefficient other than 1 over square root of m, because that's when you take the square sum, it's equals to 1. Makes sense? Yeah? Okay. So I've taken the quantum Fourier transform, the 2 to the n over 2 is, I put it in the inside of the square root, and k goes to 0, m minus 1. And here is the quantum Fourier transform part. Y from 0 to 2n minus 1 exponential 2n 2 pi I. What is it? x0 kr, that's your number x here, and y, and y. Okay. So and then what? You take a measurement, right? So let's do a little bit of modification here. We have square root 2nm, and let's put k first, or let's see. Yeah, let's put y first. So y from 0 to 2n minus 1 And I'm going to split the exponent here. Exponential 2n 2 pi I, and kry comes first. Maybe kr? No, I think x0y first. So because k is an index, I don't want to put it here. So x0y first, and then put the next summand here. K0 m minus 1 exponential 2n 2 pi I and kry. So maybe put ry first and ky. Okay. So you can imagine that this is the big sum. It's the sum of y, and there is a common factor here, and for each y, and also this is entire thing is just coefficient that is another factor of the ket y. Okay, so we have to measure it. So let's say our second measurement, C2, is Z. Okay, so then I kill everything except for when ket y is Z. So what is the probability of observing Z? Okay, so it's kind of going backward. So let's say we took a measurement Z, and we took an observation Z, and then just trace back how much was the probability of observing that number. So take a square root of this, 2n m, and then you take a big sum over this summand, and you see, since we are taking, we already take a measurement which got the measurement outcome as z, we only have y equals to z. Everything else is killed. So we don't need to look at this entire sum. We only look at the coefficient of ket z, right? So replace y by z, and then compute the squares of this coefficient part. So this is exponential 2n 2 pi I x0 z. So that's the factor, just single factor of this big sum. And then this one, k from 0 to m minus 1 exponential 2n 2 pi I ry k n square, right? Let's compute. So first one, what is the value of first factor? What is this? So this is the single complex number. There's no summand. So exponential of something. What's the size of complex number which is given as exponential of something? Yes, 1, because it's on the circle, right? It seems complicated, but it's just the angle, whatever except I is just about angle, right? It's angle times I, exponential theta I, so it's always 1. So we need to know, just compute this part. Okay? So this is equals to 2n m, and look at all, so y is set here, So look at this again. So this is geometric series, right? So this is 1 minus the common ratio, which is 2n 2 pi I r z. So that's the common ratio. And over 1 minus exponential 2n 2 pi I. K is going m, so r m z, right? Square. Okay, so now this is something. What is something different? So is this part, the numerator, is numerator 0 or not? Well, we don't know, but so in the previous situation, Rm was the multiple of 2 to the n, right? But here, we don't assume that. So which means that R can be any number in between 2 to the R, 2 to the n. Actually, it has to be less than 2 to the n minus 1, but let's say Rm is not the multiple integer, probably not the integer multiple of 2 to the n, because if it's multiple of 2 to the n, like Rm is the multiple of 2 to the n, that means you have only n out of 2 to the n chances to have such case. So that's very rare. So if you find out that this Rm, so if in a very, very small chance that your radius was actually the integer, actually was a factor of 2 to the n, then you can go back to the situation again. Like if you're convinced that your period R is the 2 to the n, 2 to the power of something, then you can do the same thing we did before. But in most cases, because it's not, you can assume that this is not equals to 1. So this is not going to be 0. So there's some chance up here. See what I'm saying? So let's say if Rm was integer multiple 2 to the n, that means you're not going to have this probability. So there's something fishy going on. You're not going to get convincing data to find the period. That means it probably that the period is 2 to the power, so you can go back to the original method. And however, that doesn't really happens at all. So you can just assume that this is not 0. So let me write it clear. So Rm is not an integer multiple of 2 to the n. Okay. So let's compute this. I'm going to use this identity. So what is 1 minus, so again, the numerator and denominator, they are the same format, which is 1 minus exponential theta I psi squared. So I want to express this in different ways. So when you take the square of its size of complex number, you take the conjugate and multiply together. So we have 1 minus exponential theta I times 1 minus exponential. What's the conjugate of this? It just take the angle reversed. So this is equal to 1 minus exponential theta I minus exponential minus theta I plus 1. So it's a 2 minus. So now let's use the Euler formula. Cosine theta plus I sine theta and minus cosine theta minus I sine theta, right? So these two cancels out, right? So we have 2 minus 2 cosine theta. And I can split cosine theta into sum because it's theta over 2 plus theta over 2. So it's 2 minus 2 cosine square theta over 2 minus sine square theta over 2. So this becomes 4 sine square theta over 2, right? So let's use this formula. So we have 1 over 2nm, and on the top, just be careful about the theta part. And 4 is common, so I can just get rid of 4. Sine square of 2n 2 pi r m z. It's complicated, but anyway. So sine square and I don't have space, so let me just write it here. Over sine square, this one is 2n 2 pi r z. Okay, so only difference is that we have m or not. Okay, so what is this? So how do you compute this? Well, we can't compute until we know what that is. We don't want to just do the computation after taking a measurement. We just want to guarantee how much probability that should be before taking a measurement or arbitrary jet. So here comes the Mermin's clever ways of computing this. So it's hopeless to work with any Z, but we're gonna assume that Z is a very special kind and assume that Z also can be written as Zj. The J is just a integer here. That it's the J multiple of 2 to the n over R plus some delta, right? So what does that mean? So Zj or Z is just an integer, right? And when you take the ratio 2n over R, it's not an integer, right? It's a bigger number bigger than 1, it's not an integer. But somehow, if you take an integer multiple of this number, and then remaining of, and then you take the largest possible integer, which doesn't exceed Z or slightly exceed Z here. And the error part between this number and this number is delta n. We assume that delta J is less than 1 over 2. So let's say, so this is 2n over R, 2n over R, and so on. So these are all equal in size. So this is your Z. It's called, this is 0, and this is Z. And then went up to this far by taking the leap of 2 to the n over R size. And the remaining part, maybe this is too big, so you went to one more step. And then this part is delta J, and luckily this delta J is less than 1/2. Okay? So let's assume that. Let's assume that and see what happens in that case. So I'm going to replace jet by this formula. Okay. So in this case, P Z is going to be 2nm and sine square 2n 2 pi r j 2n r plus delta j square. And here we have sine square of 2n 2 pi r m and j 2n r plus delta j. Okay. And then what? So look at the upper part. We have 2n, 2n cancels out. Let me just simplify it one more step here. So we have sine square r 2 pi, r is also canceled out, sorry. So r is canceled out. So we have 2 pi m j, 2 pi I m j, right? And then 2n 2 pi r m. So I'm going to write down in different ways. 2 pi I forgot I here, sorry. Also, I forgot I here. And rm over 2n. So I didn't do anything on the second part here. I only changed the order of multiplication here. That's the j here. And in the denominator, we have sine square. So r cancels out to j here. And 2 pi r, in this case, just j, right? Plus 2 pi r. Also in here, it's 2n r times delta j. Okay? So you have integer multiple of 2 pi I on numerator and denominator. You can take this away and see the remaining part. So here, what you want to find is you have Rm over 2n and R over 2n, and this R is quite large. If R is small, then I mean, even if R is small, it's impossible to find whether it's actual period or not. But let's say R is pretty small. I mean, relatively smaller than 2 to the n, quite small. But if you take the m times of the period until the end, then Rm, the difference between Rm and 2n is less than R, right? So since R is assumed to be relatively really smaller than 2 to the n, this Rm and 2n are considered to be almost same number in size, right? So this Rm and 2n is almost equals to 1 because we assume that R is really smaller than 2 to the n. Okay? And what happens to here? It's the same thing here, and this, so let me check, make sure. This R to n, it's really smaller than 1, right? So, but we don't want to make it into 0. I don't want to say it's 0 because there is something going on in delta here, but just smaller than 1. So, what? So now, what we can do as an estimate, so all we need to know is about estimate of this probability. Remember that we are taking the probability of taking a measurement of z. So we have equal to 2nm. So when this is almost equals to 1, then you can just ignore that it's almost 1, the sign of 1 times delta. So this is not the dominating factor. This is the dominating factor to determine the entire value of inside. So it's going to be sine square of 2 pi, sorry, I think I shouldn't say I, right? Sorry, why did I put I here? So you don't need I, right? So, sorry, so I is not here. So it's 2 pi delta j. And how about, yeah, so how about, is it 2 pi? Yes, it's 2 pi. And how about the denominator? We have something really close to 0 inside of sine. So when sine x, when x is smaller, almost equals to 0, not equals to 0, then you can imagine that x is almost same as sine x because we have the limit of x over sine equals to 1 when x goes to 0, right? So that's what happens in the denominator. So it's, since r over 2 to the n is really smaller than 1, almost equals to 0, so we can just ignore the sine part and then just say 2 pi r over 2n delta j squared. Okay? So, I think wait, I made a mistake here. So you have a pi over 2, so we have 2 have to get rid of. So we have no 2 here. Sorry for that. So we have 2 cancels out. So we have no 2 here. So no 2, right? So no 2 here. No 2. Okay. So let's do some computations. So what do we have? 2nm, and let's take this out. We have r squared to 2n, okay? And then the remaining is sine squared pi delta and pi delta. So look at this part first. So this one cancels out. So we have Rm 2n and 1 over r. And we get the same thing here. So we know that this is almost equals to 1, right? So at some point I should take the approximation sign instead of equal sign. So let's say approximation here. Okay. So this is almost equals to as if it's just 1, and so it's 1 over r. And how about, so this one, same thing here, so on the right. And look what we are doing here on the right side of factor. So we are doing something like x over sine x, right? When x is in between pi over 2 and minus pi over 2, because we assume that delta j is less than pi over 2. So let's draw the graph of sine. This is the graph of sine between minus pi over 2 to pi over 2. And we know that this is the line y equals to 2 over pi x, right? You see, if I take the absolute value of this, then the absolute value always must be less than 2 pi over x, 2 over pi x, right? So this is always less than this, the absolute value, right? Or just this, right? So when I take the square, it's also less than this, right? Because of this, the graph. So I know that this is less than 1 over r times 2 over pi squared. So let me just make a summary here. So what we did is finding z satisfying that equation, which we call it that j is approximately bigger than 1 over r 2 over pi squared. Okay? So how many are there? How many z are there satisfying this relation? So I could have j from 0 to r, right? J to minus r. If it's r, then it could be less than r2 to the n, but let's just count just 0 to r minus 1. So the probability that the observation z is of the form that j is bigger than what? Pz0, Pz1, and up to Pz r minus 1, right? So remember that delta j is not a variable. It's determined automatically by taking z, okay? So there's the only way, so there's this much probability to observe this kind of z. So what is this? So each of probability is bigger than this, and there are r of them. So r times 1 over r times 2 pi over 2, and r cancels out, and this is the smallest chance, and this is approximately 0.405, which is more than 40% chance. So what does that mean? So that's the final remark. If we take the quantum Fourier transform circuit like that, and if we take just the measurement, there are more than 40% chances that your z is of this form. So what about having this form? What's good about having this z? If you have this z, you can find r by continuous fraction. You need some number theory to talk about this. So once you have this, your z minus jr2n is less than 1 over 2, which means that if you just take away here, so 2n z minus j over r less than 1 over 2 times 2n here. So if you set your z or your numbers correctly, then it means that This is something you know by the measurement, right? You know what n is, you know what z is. Which you don't know is r and j, but j is not really matters. What you want to know is r. The number theory on continued fraction said if you have this inequality, then you can find j over r with a continued fraction of this number. Okay, so that's what we're gonna talk about next time. So if you have any question, let me know, and see you on Wednesday.